Welcome to the Deep Dive. Today we're analyzing a single really groundbreaking piece of research that I think fundamentally shifts how we need to approach security in voice AI. The paper is Replay Attacks Against Audio Deepfake Detection.
And it's a big one.
It really is. Our mission today is pretty laser-focused. Given your expertise in ML and data science, we're going to skip the basics.
Right.
We're providing a professional, comprehensive overview of this paper's methods, its specific findings, and what it all means for system architecture. We're drilling straight down into the data.
And it's important to frame the problem first. You know, the advances in text-to-speech and voice conversion from companies like Resemble AI, M-AILABS, they're incredible for things like healthcare and entertainment.
Absolutely.
But this is dual-use tech. It opens the door to misuse, whether that's disinformation or even high-stakes phishing and fraud. So these detection systems are vital.
There are final gatekeepers.
Yeah.
But this paper points to a critical, almost mundane vulnerability. The simple replay attack. We're not talking about complex digital perturbations here. We're talking about playing synthesized audio out of a speaker and just recording it with a microphone.
Creating a physical air gap. And the core finding is, well, it's pretty alarming.
It is.
That process of replaying and re-recording deepfake audio fundamentally changes it. That physical environment, it acts like an unintentional scrambler.
It cloaks the synthetic origin.
Exactly. It hides it from the very models designed to catch it.
So the central thesis is that this physical channel effectively makes deepfakes look like genuine recordings.
Right.
And the hypothesis has to be that the convolution effects from the speaker, the room, the mic, are stripping out or smoothing over those subtle high-frequency artifacts.
The very fingerprints that these models are trained to detect.
Precisely.
What's so impressive about this work is the rigor they applied to what is essentially a physical hack. To really quantify this, they built a new data set. ReplayDF, exactly. It was created through systematic, controlled experiments in a lab. They prioritized physical reality over just, computational simulation.
And that focus on physical generation is what makes it so valuable.
Yeah.
We're talking about, 132.5 hours of audio?
Yeah, a huge amount.
Derived from the standard M-AILABS for bona fide samples and MLAAD v5 for the original spoofed audio.
But for an expert listener, the crucial part isn't just the total hours, it's the diversity of that air gap channel itself.
Okay.
They systematically used 109 unique recording configurations.
109.
109 distinct combinations of consumer-grade speakers and various mics, all chosen to reflect real-world scenarios.
And they covered a lot of ground with the sources too, right? Spanning multiple languages.
6 European languages: English, German, French, Italian, Polish, Spanish. This helps make sure the vulnerability isn't just, language specific.
And crucially, they tested 4 major modern TTS models.
Right. BARC, VATS, and then both versions of XTTS. So this isn't a flaw in one single architecture. It's a cross-cutting failure.
So all that work results in 52,320 total recordings.
And the metadata is just as meticulous. Every single sample is annotated with not just the label and model, but descriptions of the mic and speaker, a setup image, and, this is the key part, the actual room impulse response, the RIR.wave file from that exact setup.
That RIR file is an incredible asset for future research.
It is. It lets other researchers replicate or model the exact convolutional signature of that room and that hardware. We can move beyond simple simulation.
Okay, so let's move into the experimental results. Section 2 is where they quantify just how bad this vulnerability is.
Right. The approach was straightforward. Compare performance on the baseline dataset, the original files, versus the ReplayDF dataset, so the re-recorded files.
And the metrics are accuracy and equal error rate, EER.
And their first sweep across 6 open source detection models, which is in Table 2, which reveals a generalized failure.
Every single one.
Every single model took a significant performance hit. We're talking up to 20 absolute percentage points in accuracy.
But the most revealing data comes from the top model, W2V2 ASIST.
Yeah, the one based on self-supervised learning features from Wave2Vec 2.0.
On the clean baseline data, its ER was about 10.6%, which is respectable.
It is, yeah. But then you test it against the physical reality of ReplayDF.
And the ER just surges to 24.8%.
We have to pause on that number. An ER of almost 25% means that nearly 1 in 4 deepfake attempts would just sail right through a system that we previously considered state-of-the-art.
That's a functionally broken detection system.
Completely.
And to make sure this wasn't just a fluke of one training set, they trained that same model on 5 different data sets: ASV spoof, fake or real, in the wild.
Right, this step confirms it's an architectural vulnerability. And even the best configuration, the one trained on ODSS, which got a very tight ER of 4.7% on its baseline.
Even that one couldn't handle it.
Not at all. When they tested it on ReplayDF, its EER plummeted to 18.2%.
A drop from 4.7% to 18.2%. I mean, that's catastrophic. It turns a reliable system into something structurally insecure against the most basic physical attack.
It really suggests that the features learn through self-supervision. While they're great at picking up digital artifacts, they're just inherently fragile when you subject them to real-world acoustic transformations. The physical channel is just outside the manifold of variations they were trained on.
Which leads us right into Section 3, dissecting the attack mechanism. If performance is dropping, we need to know why. Are we getting false positives or false negatives?
And Table 4 makes this incredibly clear. When they looked at bona fide or genuine audio in the ReplayDF set, the accuracy stayed remarkably high, around 97.7%.
So re-recording genuine speech does make it look fake.
Exactly. The error gap itself isn't creating synthetic fingerprints. The failure has to be on the spoof side.
Okay.
And it is. The entire performance drop, between 28 and 42 absolute percentage points, was seen only on the spoofed instances.
So the conclusion is an overwhelming increase in false negatives.
That's it. The convolutional effects are scrubbing the synthetic evidence, and the detection model is completely fooled.
So then they investigate whether the severity of this failure correlates with the audio quality. Does a bad-sounding replay make for a better disguise?
Right. They used PSQ for objective quality and human-rated MOS scores for subjective quality. And they made sure the ReplayDF samples covered a huge quality range from nearly unintelligible to crystal clear.
And the data confirms a significant link. Detection accuracy correlates positively with both. The Pearson correlation was 0.423 for MOS and 0.509 for PESQ.
Which has immediate practical implications. It means the more aggressive the physical attacks are the setups that introduce more distortion and get lower quality scores.
The more effective the attack is.
The more effective it is at masking those artifacts, leading to worse detection. So a high distortion replay is a better attack.
But that raises the crucial question. Is this just because the audio quality is worse in general, or is it something specific about the physical channel?
And this is the essential distinction the paper makes. Section 4.7 nails this down with a test against simple additive noise.
Okay.
They took the clean baseline data and just added standard noise Gaussian, white, pink at different SNRs to simulate general quality loss.
And the finding here is the real nail in the coffin for the it's just noise theory.
It is. The W2V2 ASIST model's performance was barely affected by that added noise. The accuracy only changed between -2.3% and +3.1%.
So it's not the noise.
It is not simply generalized quality loss. It strongly suggests the air gap works because the physical channel performs a convolution operation, which is fundamentally different from adding noise.
Right. Convolution smooths out the residual features the detectors rely on. Additive noise just corrupts the signal without structurally changing that synthetic fingerprint.
That is the pivotal takeaway for anyone designing these models. The challenge is structural transformation, not signal masking.
So given this massive vulnerability, they had to look at mitigation. Could augmenting the training data with those captured room impulse responses, the RIRs, help?
It helps, but we have to be very cautious with that word.
Okay.
RIR augmentation did reduce the impact. It improved the overall EER from that disastrous 18.2% down to 11.09%.
Which is an improvement.
It is. And if you look at the specific attack types, accuracy went up by a good 10 to 15 percentage points across all the TTS models.
But hold on, an EER of 11.09% is still more than double the model's original baseline failure rate of 4.7%.
Exactly.
We can't call that a success. The system is still functionally compromised compared to its performance on clean data.
And this is the key insight for practitioners. RIR augmentation is the best defense they tested, but it falls severely short. It helps the model generalize to things like reverb, but it doesn't capture the full complexity of the transducer effects.
The specific changes from the speaker and my hardware?
Precisely.
So what does this all mean for us as architects of these security systems? The paper establishes that replay attacks are a highly effective, very real threat. And the core failure is the removal of artifacts via acoustic channel convolution, which is a totally different problem than standard noise.
And critically, the research community now has the tools to tackle this. The ReplayDF dataset, with all its metadata and RIRs, is publicly released for non-commercial use.
This moves the field from just digital forensics into required acoustic modeling.
It has to. Our feature engineering pipelines can't just focus on residual digital artifacts anymore. They have to incorporate robust, high-fidelity models of the physical channel reverberation, distortion, all of it.
We're fighting acoustics now, not just code.
Which brings up a really important question for future work. We've confirmed that simple additive noise augmentation fails, and RIR convolution is only a partial fix. So what specific nonlinear modeling techniques, beyond just generalized acoustic models, are we going to need to achieve full robustness against this kind of weaponization?
How do you build detector features that are truly invariant to the physical channel?
That's the question.
An excellent point to end on. The paper has defined the problem with incredible precision. Now the real scientific engineering begins.